Okay, yeah, so you're right, Trevor. A ionic compound is when you start, the first element is a metal. If the first element is a non-metal or a metalloid, then we do covalent naming. Ionic bonds are when there's an unequal sharing of electrons. One element transfers its electrons to another element, and that's why you get a cation, the thing that lost the electrons, and an anion, the thing that gained the electrons. Metals give up their electrons, forming a positive charge. Non-metals gain electrons, getting a negative charge. So here, arsenic, As, it's right there, and it's a little borderline. You might be a little confused, like, oh, will that be a metal, non-metal? That's actually going to be, we're going to consider that as a non-metal, okay? And so we're going to be doing our covalent naming. When you do covalent naming, that's when you use the prefixes. So you see a 4 right there. You have to memorize the prefixes. So what's the prefix for 4? Middle? Good. No? Yeah. That's okay. Sure. Tetra. So you would say tetra arsenic. Now you don't change the ending of the first element to "ide." It's only the second element. So you say tetra arsenic, and then what's the prefix for 10? You can just say it out loud. Deca. Deca. Whenever you could say either deca oxide, or typically you'll see people drop off that A when it's paired with oxygen and just say dec oxide. The answer, well, you're not doing a formative, but if you were doing a formative, I would give it to you both ways. Okay. All right. So then looking at number 2, so look at that first element. Ask, is it a metal or a non-metal or a metalloid? So V is vanadium. That's going to be a metal. Now, when it's ionic, you then have to ask another question. Is that metal a transition metal? Because if you look at our periodic table up there, you don't see an orange sticky note above your transition metals, groups 3 through 12. That means that transition metals form more than one ion. And we have to specify what kind of ion they form using those parentheses. So vanadium is a transition element. So we would say vanadium, and then we're going to use parentheses to say what the charge is. But we're going to have to calculate that charge. Like it's something that we have to figure out using our formula. Notice how we don't say divanadium. The hardest thing is like whenever you get done doing a problem that was covalent naming, and then you move to one that's ionic naming, everyone start using prefixes again. You don't use the prefixes unless it's a covalent compound. All right. So then you wouldn't use a prefix for the 3 there. You just say vanadium something oxide. So let's calculate that something. The charge on oxygen is -2. And the shortcut when you're doing these, so like if you have 3 -2s, like times 3, that gives you a -6. The shortcut with this is whatever the number of like oxygen atoms there are here, that's going to actually be the charge of the vanadium. Whatever the charge is on the vanadium, or the number of vanadiums, that's the charge of oxygen. You see that? So like we have 3 oxygens, that's why vanadium's a +3. We have 2 vanadiums, that's why oxygen's a -2. So it's kind of a shortcut you can use to know that it's vanadium 3 oxide. If that's confusing to you, you could just do it the other way we've been doing it, where we were saying you got to cancel out a -6 charge to get our charges to go to 0. You have 2 plus 3 charges. If you have 2 vanadiums, each vanadium needs to be a +3 to cancel out the -6. Okay? So that's kind of like the shortcut you could do. All right, ammonium phosphate. Anybody want to take a guess about what you think? What was ammonium? Well, first you want to figure out, is this ionic or covalent naming? And this one's a little bit tricky because you look at it and you're like, well, ammonium, that's one of your polyatomic ions. So ions, polyatomic ions, they have charges, that's going to be ionic naming. So you would just tell me what ammonium is, and you got to memorize that. Let me use a different color. You got to memorize that ammonium is NH4, and we know it's got a +1 charge. And then phosphate, that is PO4, and that has a -3 charge. Charges have to add up to 0 because this is ionic naming. 1 minus 3 is not 0. So we need to have 3 plus 1s to cancel out that minus 3. How you represent that in the chemical formula is you have to put parentheses around NH4 because it's a polyatomic ion, and then you would put a 3. We need 3 NH4s. If you don't have the parentheses, you'd be saying that you have 1 NH43, which is ridiculous. That doesn't exist. Okay. All right, so there you go. Let's do the last one, sulfur trioxide. So you look at that and you're like, well, sulfur, is that a ionic or a covalent compound? Well, sulfur, is that a metal or a nonmetal? Sulfur is going to be a nonmetal. So that means we're doing our covalent naming rules. So we would just say, if you don't see any prefix with her, you assume it's just one sulfur. Remember, you don't put mono when it's the first element. So you don't say monosulfur, you just say sulfur. And then tri, that means 3. And oxide is referring to oxygen, so it'd be SO3. Okay? So, yeah, we'll do a little more practice with naming next class when we do the test review. There you go. Hopefully by now it's sinking in a little bit and it's getting to be a little more kind of automatic for you. All right, so getting into the new stuff. So if you got your note packet, you can pull that out and start filling this slide in. The main thing we're focusing on today is percent composition. We're actually going to do a lab today. We're gonna do a reaction, and you're gonna calculate how much carbon dioxide did you release, and find the percent composition, and that'll make a little more sense when I get into the notes. Before we actually talk about percent composition, there's one actually two concepts we actually haven't gone over. It's basically just kind of a couple things to memorize, and those are acids. This first slide is really just kind of things we've already talked about here, like use prefixes. If you're doing covalent naming, use prefixes. Still change the ending to "ide." But now, if it's an acid, if you see an element that starts with H, that's going to tell you it's an acid. So, for example, these are the acids you have to memorize. Hydrochloric acid. The name of it kind of tells you what it is. Hydro, hydrogen, chloric, chlorine. So HCl is hydrochloric acid. Sulfuric acid. You hear acid, you're like, oh, it must start with H. It's H2SO4. Now, I have a question for you. Notice how there is one hydrogen in hydrochloric acid and 2 hydrogens in sulfuric acid. Why? You just got to blindly memorize that, or could you use what you already know about chemistry to figure that out? Amelia? They got a balance. Good. Chlorine has a -1 charge. Hydrogen has a +1, so that's going to add up to 0. Sulfuric acid is using our polyatomic ion sulfate. You should know that sulfate has a -2 charge. We already said that hydrogen's a +1, so that's why you have 2 hydrogens. In other words, if you know your polyatomic ions, naming these acids really actually isn't that big of a deal. It's actually really just, it's almost like more free points that comes from you memorizing those that list of polyatomic ions. Okay? So finishing this out, nitric acid is HNO3. Notice how nitrate's a -1 charge. That's why it's just 1H. Carbonic acid is the carbonate ion, which has a -2, and then that's why you have 2 hydrogens. And then finally, acetic acid, that's the acetate ion, where it has a -1 charge. And there's 2 ways you'll see it. You'll see it either in a longer way written like this, or written like this. Now, notice how these are the same. Here there are 2 carbons, and there 1, 2 carbons. There's 3 hydrogens, 3 hydrogens, 2 oxygens, 2 oxygens. I'm not going to force you to write it one way or another, but you need to be familiar seeing it either way. On a test or assignment I give you, if I show you in that form, you should still be able to know that's acetic acid. So there you go. Is there any questions about the acids? As I said, if you know your polyatomic ions, it's really not much more to add on. I just didn't want to throw that in there because, until like after the break, just to make things a little simpler for you. Okay. And this slide, this is a good summary slide. So like going over ionic naming, metal plus nonmetal. Remember, another way of saying that, a more general way of saying that, is cation plus anion. Because not all ionic compounds have a metal first, aka like ammonium. Ammonium is a cation, it has a positive charge, but technically nitrogen's a nonmetal. Okay? And then you balance the charges. Covalent, nonmetal, or metalloid plus a nonmetal, and that's when you use your prefixes. And then acids, they start with an H, and then these are the acids you got to memorize. Now, the last bit of thing that you have to memorize, and we've actually already learned it in a different unit, is the diatomic elements. And that was, like I told you, the have no fear of ice cold beer, the H2, N2, F2, O2, I2, Cl2, Br2. They exist paired up. So I've shown you this slide before. It's like that L shape on the periodic table. So all of the halogens, oxygen, nitrogen, and hydrogen, those are going to exist diatomically. So if I ask what is the chemical formula of chlorine, you would say Cl2, not just Cl, because chlorine exists in nature paired up with another chlorine atom. Okay. Now, why would that make sense, especially for the halogens? They would exist like paired up with another, with a partner. If you think about like the charges they have. So if you look on the periodic table, we say the halogens form a -1 charge. So if they were to like kind of lean on each other and share an electron, that would help them have a full outside shell of electrons. It's like if you're missing a leg and they're missing a leg, you can kind of lean on each other. Okay. And then here are some other mnemonics if, the have no fear of ice cold beer doesn't work for you. I have no brighter clever friends is another fan favorite. Okay. All right, percent composition. This is, it's mathy. I think it's fairly simple. It's this formula. Percent composition. Well, let me tell you the idea of it. Let's say you have a compound. Like you have a compound H2O2, and I want to know, well, what percentage of this compound, what percentage of the mass of that compound comes from hydrogen? That's percent composition. You've seen problems like this like in math class, where like, oh, you're eating some M&Ms, and they tell you like, there are 20 red M&Ms, and you have a total of 100 M&Ms. What percentage of them are red M&Ms? What would you say? 100 M&Ms, 20 are red. What's the percent composition of red M&Ms? 20%. That is all you're doing in chemistry, but instead of M&Ms, we're dealing with compounds. And instead of like colors of M&Ms, we're dealing with different elements. Okay? But it's really a pretty simple idea. And it should make sense to you, hopefully, once we go over a couple practice problems. But here's the formula you would have to memorize. And I say memorize, I think it's something you can really reason through. You take the mass of the element, the mass of the compound, this would be like the number of M&Ms, of a color, divided by the mass, or the number of total M&Ms, times 100, because that's what you have to do to get something in a percentage. Kind of like when we did like percent error. When you multiply by 100. All right, we good in this slide? All right, so let's go over an actual example. So here, they give you the molecular formula of a butane, and they're asking, first step, what is the mass of carbon in 1 mole of butane, of C4H10? Remember, a mole of something, a mole is just a number. That was Avogadro's number, which is 6.022 times 10 to the 23rd. Fortunately, you're not really working with Avogadro's number. I just wanted to remind you that's what it is. 1 mole of butane means you have that many individual molecules of butane. What you got to do is find the mass of carbon. How would I know what the mass of carbon is? What's the mass of carbon if you had that many carbon atoms? Think back to like, I think Unit 3 or Unit 4. Sure? You just look at the mass number. So the mass number of carbon is 12. So when they say the mass of carbon in 1 mole, well, that's going to be 12 grams. But when they say that would be 12 grams is the mass of 1 mole of a carbon, of just one carbon atom. Here's the deal. In C4H10, you have 4 carbon atoms. So we're going to have to multiply this number by 4. Because there are 4 carbon atoms in C4H10. So it's going to be 12 times 4, which is 48. So there are 48 grams of carbon in 1 mole of C4H10. Okay? And a more like detailed way of saying that is there are 4 moles of carbon in C4H10. Okay. Now the mass of hydrogen in 1 mole of C4H10, well, what's the mass of one hydrogen atom? Or not one hydrogen atom, but like a mass of 1 mole of hydrogen atoms. It'll? 1. You got 1 gram. And then you want to multiply it by, well, how many hydrogen atoms do you see in C4H10? 10. So you do 1 gram times 10. So you would get 10 grams of hydrogen atoms in 1 mole of C4H10. Now then they want to know what's the molar mass. So, because we go back to our formula, we found the mass of the element in that compound. Well, we got to find now the mass of this entire compound. Well, all you got to do is just add up these two numbers. The molar mass of C4H10 is the mass of those 4 carbon atoms that we found here and the mass of those 10 hydrogen atoms. So you would do 48 plus 10, that would give you 58 grams. That would be the molar mass of C4H10. Okay? Now then, what is the mass percent of carbon in C4H10? So to figure that out, take the mass of carbon in that molecule, which we said was 48. So you would do 48 grams divided by the total mass of that compound, the total mass of the butane, which is 58 grams. And then you times it by 100 to get into a percentage. So 48 divided by 58 times 100 is something. You're going to use the 10 grams when you find the mass percent of hydrogen. 82.75? Yeah, all right, cool. So the mass percent of carbon is 82.75%. Now use common sense here. Go back to your M&M example, right? Carbon is much more massive than hydrogen, right? It's 12 times the mass of hydrogen, and there's still a decent number of carbons compared to hydrogens in that molecule. That's why the majority of the mass of this molecule comes from carbon. Okay? Now the mass percent of hydrogen, take the mass of hydrogen in that whole molecule, which we said was 10 grams, divide it by the mass of the whole molecule, which was 58 grams, and then times it by 100 to get to a percentage, and that should be the remaining percent from 100. So that should be 100 minus that number. So 17.25? 0.4. 24. We'll say 17.25. Kind of like when we were doing like the mole calculations. Some of this depends on like how you round. 2 decimal places is like, kind of typically the accepted thing. Technically, there's sig figs, but we don't really worry about that in non-honors. Yeah, go ahead.
So like for the other one, if it was like 82.75 would you just do like 82.6 or
Whatever would be rounding up. Like if it was like, if like you have a third decimal place that's a 5 or a 6, you would round that number up, the second place up. If it's below 5, you would round it down. Possibly, but it's not a huge deal one way or another. Now, notice, you did this right because these two numbers add up to 100%. Now, you got to keep in mind that this molecule had 3 elements in it, but some molecules might have like, this compound, this molecule had 2 elements. Some compounds could have 3, maybe 4 elements. So you got to keep that in mind. You can't just do like 100 minus that to get the other elements, because that wouldn't add up to 100. All right, let's do one more problem. So let me get this erased. So this time they're asking, what is the percent composition of hydrochloric acid? So hydrochloric acid is one of those acids I told you to memorize. Well, step 1, find the molar mass of all the elements. Okay? Well, hydrogen, what is the mass of hydrogen? We do for hydrogen. We said it was 1 gram. Let's multiply that by the number of hydrogens in our compound. So there is only 1 hydrogen in hydrochloric acid. So you would multiply it by 1, which really you're not doing anything to it. 1 times 1 is just 1. There is 1 gram of hydrogen in that entire molecule. Let's do it for chlorine. What is the mass of chlorine? 35, we'll say 35.5. 35.5 grams. Multiply that by the number of chlorines in that molecule. Just 1. So really it's just going to stay the same. So it's a little bit easier for this molecule because you just have 1 of each thing. Now then find the molecular mass of the whole molecule, HCl. So that's where you're going to add this number and this number together. So the molecular mass would be 1 gram that went with the hydrogen plus the 35.5 grams, and that's going to give you 36.5 grams is going to be your molecular mass of HCl. Now then, let's find the actual mass of each individual element. So for hydrogen, you would do on the top of your fraction, you do the 1 gram, that's how much the mass of hydrogen in that whole molecule, divided by the mass of the entire molecule, which is 36.5 grams. And then you're timesing that by 100 to get you to a percentage. So 1 divided by 36.5 times 100, that should give you approximately 2.765%. So a really small number because hydrogen is a really small element. And then for chlorine, you would do on the top of the fraction, it's the mass of chlorine in that whole compound. So 35.5 grams divided by the mass of the whole compound, the 36.5, and then times it by 100 to get it into a percentage, and that should give you the 97.235%, or something around there. The number can change slightly depending on how you round. Any questions on this? There isn't really much where it gets more complicated than this. So the lab you're doing today, it's a little bit more complicated than maybe like perhaps you'll see like when you see the actual test problems, but it's to try to make it kind of a more fun lab. I gave you a couple more percent composition problems on the very back of it that are going to be more similar to actual test questions. So let me get this recording stopped.